Good morning, guys. So in this video, we will be looking at your chapter number 11, which is the analysis of variance. In other words, it's also known as ANOVA. And in this chapter, we will be looking at the F distribution. So what is the F distribution and why is it useful? So before we actually go on and learn about what the F distribution is, blah, 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 let's actually try and figure out where it is used. Okay. So remember in your previous chapter, so this is a quote directly from your chapter number 10, right? So in chapter number 10, we compare different samples and they might have this known population standard deviations, or you might also have unknown population deviations, okay? And we use the pool sample T statistic, which is this, and having a pool sample variance and so on. So, but if you zero in over here, why do we need the pool, the standard deviations? Because we do have an assumption that the two populations have equal standard deviations, and we use that best estimate in order to compute the pool standard deviation. So the big assumption is that the two different populations, or the two samples which you're comparing, have equal standard deviations. But how do you test that? Well, that's where the F test comes into play. So the F distribution, in some sense, is a family of distributions. It looks like this. It has 2 degrees of freedom, and because when you're comparing two samples, you have 2 degrees of freedom, degree of freedom for each sample in some sense. And if distribution is continuous, it cannot be negative. So the lower bound limit is 0. It is positively skewed for the most part. It's never negatively skewed, and it's asymptotic. This line almost never reaches the 0 level of frequency again. So these are some characteristics of the F distribution. And you could use this F distribution to try and test a hypothesis, to try and see if two samples or two populations, in some sense, if they have similar variances or standard deviations, right? So the way you try and do this, let's actually look at an example. So by the way, the test statistic, in some sense, is just the variance of the first sample divided by the variance of the second sample. Here, you're assuming if the variance of one sample is greater than the second sample, and the one with the higher variance always goes on top. That's very important. If your second sample has the higher variance, you have your second sample go on top and the first sample go on bottom, and this gets flipped. Okay, so that's a simple scenario. So let's look at a simple example over here. There's a meat packing plant, or it packs a lot of cartons with jars, and one machine can potentially pack a lot faster than the other machine, and you're using a 0.1 significance level. And we're trying to see if there's a difference in the variation of the packing time using the two machines. So we have all the times here for one machine, more data for the second machine, and your hypothesis is the variances are equal, and the alternate hypothesis is they're not equal. It's a two-tailed distribution, two-tailed test, and the significance is at 0.1, but when you split it into for a two-tailed test, it will be 0.05 when you're looking at the table. So the appropriate test statistic is Sn squared by S2 squared, where S is the sample standard deviation and Sn squared is the sample variance. Okay, so when you actually compute these things, this is the idea of the decision rule in some sense. That's your step 4. And this is given in your tables. So this is your appendix B7. So your F table, in some sense, is given in, oh, it's hanging up. Well, I'll tell you, the F distribution this table has like the degrees of freedom for the numerator in one column and degrees of freedom for the denominator in another column, as shown in your slides over here. So degrees of freedom is in one column and the degrees of denominator in this column. And so if you look at this particular sample, the degrees of freedom for the new machine, you have 1, 2, 3, 4, 5, 6, 7 observations for the new machine and 8 observations for the old machine. So your degrees of freedom for the new machine is going to be 7 minus 1, which is 6. And for the old machine, it's going to be 8 minus 1, which is 7. And you go 6 and 7, and the corresponding F critical value of F statistic is 3.87. So what does that mean? When you find out your own test statistic, and if that is greater than 3.87, you reject the null hypothesis. And if your F statistic is less than 3.87, that means you accept the null hypothesis, or you do not reject the null hypothesis. And so if you reject the null hypothesis, that means the variances are not equal. And if you, right, so in some sense, go ahead and actually compute the variances. So once you compute the variance, you could easily compute this in your Excel. It's the same formula for variance which you've been using all along. And you compute the standard deviations over here. And the variances would just be the squares of the standard deviations. And that is 5.45. So since our F statistic over here is greater than the critical value of 3.87, we reject the null hypothesis that the two variances are equal, and we accept the alternate hypothesis, which is that the variances are unequal. Okay, so and now that you know this, you could go ahead and perform some other tests. But you do know that these are not comparing apples to apples in some sense, because they are very different machines in some sense. Okay, and they're different populations as well. And we could also try and use this for something similar when we're trying to find out the distance which you want to use to go to the airport. So this is the Google Maps, and let's say you live somewhere near the Costco, a little bit above. One of my friends live in this area, and so I just used her house as a reference. And so there are two ways to go to the airport from around the Sarnia Road all the way to the international airport. So one, you could take the Oxford Street, and the other way you could use the Windermere and Huron Street. And let's say you could go all the way up to like Fanshawe. There are multiple ways, and you come across an argument, and I don't know, husband argues that, oh, Fanshawe is a lot faster. Wife argues that, well, no, Oxford is a lot faster. It's a lot more direct. And husband says, well, that has a lot more traffic as well. And blah blah blah. They argue. So let's try and settle this argument. Like, first of all, we have to try and see if the standard deviations are similar, if there are similar populations in some. And if they're not, that means one is definitely more, has more variation than the other. So here I just came up with a sample of times, the distance to the airport if you take the Fanshawe Road, and distance to the airport if you take Oxford Street. So once you have these, you could compute your variances and your F-test exactly the same way. So H0 is that the variances are equal. Okay, and H1 is their variances are unequal. Okay, so same H0, H1 dilemma. Let's say we could use a 5% significance or 1%, 10% significance as well. And you compute your means. You could compute your sample mean, standard deviations. Let's say variance of the first sample, this, and variance of the second sample, is 2.2. And once you compute the variances, if your initial intuition is the Fanshawe is longer than Oxford, and then the F statistic is going to be 3.7 divided by 2.2. And this is 1.68. So this is the F statistic which you computed. And if you want to try and figure out the degrees of freedom in some sense, the degrees of freedom are 4 for both scenarios. So let's go to the same table from your PowerPoint. And let's look at the table. So the degrees of freedom is, well, it's actually a lot smaller here. So, but you see that it's not shown here, but when you go to the table and actually look, degrees of freedom of 4 and degrees of freedom of 4, the critical value is 6.39. So that is our critical value. So critical value tends to be 6.39. And because the critical value is 6.39 and our F statistic which we computed is not greater than the critical value, we cannot reject H0. So this is accepted to be true. It is accepted that these two variances are somewhat similar. Okay, so this is, you could try and use the F test for multiple things, but the examples over here in this video show the difference about comparing two different variances and two different populations and testing their variance. And I'll talk more about the ANOVA and the analysis of variance and what else it can be used in the video.